Okay, make sure our phones are away, as well as homework out. Let's go through this, if you don't mind. So we're on 1-4. So as we progress our ways through statistics, there are some that I think we as a whole class will struggle with, and some that we could argue, and it's fine. It's totally fine. So on problem number 1 on 1.4, I would also make that third column on the table for the total of male females. So you'd have 37 as the first one, 13 as the second one, 45 as type O, type A, B is 5. Also sum it up to 100. So I think that's important to realize that not all the columns are finished on that first problem. So just make sure that's taken care of. And then I will leave my answers as fractions. Again, I will have them as non-reduced fractions. You can reduce your fractions. You can make it decimals if you'd like. But it's your choice. Any of those answers will be accepted. So is there any questions on problem number 1, A through G, that you wanted me to go over? G? Okay. Anything before G you'd like to go over? Answer to D is, what is the problem? 67 over 100. So just letter G. All right, letter G is a good problem. So it says, R being a male and having type below independent events of each other. Okay, so you want to do this. You want to find the probability of being a male in our survey, and then you want to find is the probability of being a male such that type O is, if this creates two equal events, then they are independent of each other. So the probability of being a male, it looks like on our thing we have 40 men out of 100 people, so that reduces to 0.4. Are you okay with that? That should be pretty simple. And then we're going to go probability of a male such that O. Okay? So type O people is 18 and 27 added together, which gives me 45. So remember, this part is my denominator. And the probability of being a male in that group is 18 out of 45. Does somebody have a calculator real quick? Just go 18 divided by 45, please. Thanks, Cupcake. 0.4? 0.4. Is 0.4 and 0.4 the same thing? So these both match. So these are independent of each other. Okay? Excuse me. Uh-oh, Lenny. Okay? Is that it? Who else? Letter G, does that help? All right, next one. Shh. Couple guys over here, especially the one from Parker, are talking too much. Don't start giving him bad things. All right. Next one. Using the tables, assume two different people will be selected from the population of people who are participating in the survey. Calculate each. Both selections are male. Are you okay with this next portion? So letter A on the next portion, you have 40 out of 100 times 39 out of 100 or out of 99. Multiply that together. Both selections will be type B male. So letter B is going to be 7 out of 100 times 6 out of 99. Why is it going down on the second one? What am I not doing with the person? Yeah, I'm not throwing them back in the population. I'm saying, come here, and you come here. Okay, well, you, and then you. Letter C, both selections will be either type A or type B. Well, half of them are that, and then if we select one that happens to be that, then we're going to go to that, so then multiply that out. And then letter D, at least one of the two will be type O. At least one of the two will be type O. Okay? So what I'm going to do is I'm going to go 1 minus the 55 out of 100 who 55 out of 100 happen to be A, B, or AB. And then I'm going to multiply that by 54 out of 99. So I'm doing the complement of not having type O, and that would then tell me who has type O. Good so far? The 55 out of 100? Okay. So what I'm looking at is at least one of the two will be type O. So I'm going to look at the number of people who do not have type O blood. So I'm going to add the 37, the 13, and the 5 together, and that'll give me 55 out of 100 people do not have type O. And then I'm going to say my second person, I'm also going to check to see that does not have type O, which is 54 out of 99. So I'll multiply those two fractions together, and I'm then going to do the complement of it. So if I do the complement of it, that tells us that they don't have, or they're not A, B, or AB. And that would give us a type O. Yeah?
Okay, and I was going back, but for 1F, what is the probability of this type E given male or female? So would you just do type E females, or would you do the whole total?
Okay, so the denominator of that's going to be 60 because you're talking about 60 females. So this is like saying, all right, all you ladies in this group of 100 people, come over here. Who has type B? And so it would be 6 out of 60, which is 1/10. This is 0.1. We okay on that first page so far? All right. Flipping over to page 2. Looks like all of our rows and columns are completely filled out. So probability of traveling with a child, you're talking about 72 out of 420 people. Probability of being searched, you're talking about 175 out of 420 people, so you're working with the whole group. Letter C, probability of traveling alone and being searched. So you know that if you travel alone and you're being searched, you're traveling alone, no children, and your search is 145 people out of the 420 total. Okay, so that's just a specific number. The probability of not being searched, so you're going to go to your no column total out of your total number of people, so 245 out of 420. Letter E, not being searched such that traveling with a child. So you're going to go children. You're talking about, okay, all of you people that are traveling with kids, come here. They come here. Okay, there's 72 of you. That's our denominator. Now we want to figure out the probability they were searched. That's 42 out of the 72. So we're not looking at the whole. We're specifically taking a portion of the population out of there. Oh my gosh, you have a Grateful Dead shirt on. You're my favorite person today. Love it. All right, probability of traveling with child given you are searched. So we're going to take all the 420 people standing there. You say, hey, if you were searched, whether you have kids or not, get over here. So all the people who were searched, come over. Leave all the people who weren't searched over there. And we're going to say, okay, how many of you had kids and were part of the search group? That's 30 out of 175. Are being searched and traveling with child disjoint? No. You can be traveling with kids and be searched. Okay, there's an overlap. They're not disjoint events. And then, does it appear that being subjected to an additional search is independent from traveling with children? So we're going to say probability of search, is that equal to the probability of search such that you have a child with you? Okay, so we're going to figure out the fractions of each. If the fractions are equivalent fractions, they are independent events of each other. So the probability of you being searched is 175 out of 420. The probability of you being searched such that you have a child. So if you look, you have children. There's 72 of you. And if you're searched with a child, that's 30 out of 72. This gives me 0.416 as a decimal. This also gives me 0.416 as a decimal. What do you think? Independent or not? They are. These are equal, so these are independent events. They are independent. They are not disjoint. The disjoint just means that just because you have kids doesn't mean you can't be searched. Okay? They are in the same category. Obviously, people that are surveyed were searched if they have kids or not. Okay? All right. Can we move on to tree diagrams? Tree diagrams are another method of looking at statistics. It makes it a little bit better sometimes to look at. Tree diagrams work nicely. So, So let's start out with this first example. I want to create a tree diagram. It says we have red marbles, we have blue marbles, and we have yellow. Do you agree? Seem okay so far? Do you see how there's little branches so far? It's going to create a tree. Okay, so how many total marbles are we talking about? There's 6 total marbles, in which 3 out of 6 are red, 2 out of 6 are blue, and 1 out of 6 are yellow. Now, eyes up here real quick. This is something I want you to understand. This is why I don't like to reduce fractions in statistics. Every branch has to add up to become a whole. Okay? 3 out of 6 plus 2 out of 6, that's 5 out of 6. 5 out of 6 added to 1 out of 6 is 6 out of 6. Is 6 out of 6 a whole? Yes. This is a true tree diagram. It exists. Okay? A lot of people will make an error in statistics saying, oh, dude, I got to reduce 3 out of 6. And then they're dealing with half and a third and a sixth. And it's like, does that add up to 1? I don't know. I suck at adding fractions. Okay? So don't go and make them reduce fractions. It's fine if you do, but realize on tree diagrams especially, it's going to affect you. So you are drawing, you're going to be drawing you're drawing 2 marbles out of this particular thing. Lenny, put your phone away, please. Okay, so my next branch, I'm going to have this. I have red, I have blue, I have yellow. I have red, blue, and yellow. I have red, blue, and yellow. Does that make sense so far? It's because you're drawing 2 marbles. So if I were to draw a red and a red, it would go along with this branch. If I were to draw a red and then a blue, it'd be this branch. If I draw a red, then a yellow, this branch. If I draw a blue, I go to this branch and then have the same choices. If I draw a yellow, then I still have these 3 choices. Okay? But some of the branches might become 0 eventually. So let's go through the stats and think about it. If I have drawn a red marble already, how many red marbles are left? 2 out of how many? 2 out of 5. Good. Do I still have the same number of blues if I drew what red first? So that's what? 2 out of how many? 5, because I'm taking a marble out. And then I still have a yellow left, so I have 1 out of 5. Now, I'm going to take these branches. I'm going to make these a little bit longer just so we can. So if I draw a blue, how many reds do I have left? Out of? 5. If I draw a blue and I want to draw another blue, what do I have here as a fraction? 1 out of 5. If I draw a blue, how many yellows do I have? Is that okay? So I extended this so you can see the fraction moved out to the side rather than cramming it all together and you're squinting going, is that a 3? All right. If I draw a yellow marble, how many red marbles do I have left? 3 out of? Okay, if I draw a yellow, how many blues do I have left? Out of how many? Okay, if I draw a yellow, how many yellows do I have left? Out of? Okay. So that's the next step. Now you're going to look at that going, I thought you said those all have to add up to be 1 in order for it to be a true event. Yes, but what we have to do is we have to multiply each of the fractions together in order to make it work. So I'm going to go 3 out of 6 times 5 out of 6, which is going to give me 6 out of 30. And then this branch, 3 times 2, that's going to give me 6 out of 30 as well. This branch is going to give me 1 out of 30. Or excuse me, 3 out of 30. You see how I just did that? So I took this probability times this probability to give me, there's 6 out of 30 outcomes that could take place that would allow me to have a red and a red. Okay? If I go this way, I'm going to multiply 2 over 6 times this, so that's going to give me 6 over 30. This one's going to give me 2 out of 30. This is going to give me 2 out of 30. If I take this branch, that's going to give me 3 out of 30. This is going to give me 2 out of 30. And the last one gives me what? 0 out of 30. And make it a point that you are writing that down. Don't be like, it's just 0, who cares? No, it means something. So now all of those fractions need to add up to be 30 out of 30 to be a whole. So if we go through it, I have 6 plus 6, that's 12. Add another 3 to that, I get 15. Add another 6 to that, I get 21. Add 2 to that, I get to 23. Add 2 more to that, I get 25. Add 3 to that, I get 28. Add 2 more to that, I get 30. And if I add 0 to 30, I still get 30. So is this a true tree diagram? Yes. 30 out of 30 is a whole. It matches up. It will work out. We have all of our events to take place. So this is going to allow us to answer the rest of the question. Should I go ahead and reduce those fractions? It's not necessary. Okay? And I'm sorry that your elementary school teachers indoctrinated you to think, let's reduce a fraction. Okay? It just became a mode of thought that went with an event that didn't really make that big of a deal. I'm going to split this screen so we can start answering some of the questions, if that's okay. All right. Probability, you have 1 yellow. Probability of 1 yellow. I'm drawing 2 marbles out, but what branch would give me the probability that I have 1 yellow? Yeah. So I have 1 out of 6 probability. Done. I actually just looked right here. I was like, boom, yellow, boom, 1/6, done. Okay, B says the probability that we're going to draw a red first such that this was a blue, such that the second was a blue. Okay? So let's think about this. The first was a red. That's 3 out of 6 times the second was a blue. Which branch am I looking at? 6. It comes to 6 out of 30 because 2/5 is here. So at first, boom. So that's a 6 out of 30 event. Or 1/6 if you want to reduce it. Probability of 2 reds. Look at our thing. Which branch gives us the probability of both being red? The very top one, right? So I have 6 out of 30, red, red. So that's also 6 out of 30 because that's this branch here. Here to here. Probability first blue, second yellow. Blue, then yellow. Okay, which branch am I going to choose in order? What's my first branch to choose from? The blue one, so it's the middle one. And then I want to go to yellow. Where does yellow go from here? Down. So it's a 2 out of 30. Or 1/15 if you that person. No yellows. No yellows. No yellow. Okay? Which branch am I automatically eliminating on the black branches? The yellow one. So now I'm only interested in these 2. Okay? I don't want any yellows to be drawn. So these 2 are fine as long as I don't go yellow. So I know this one will work. So I get a 6 out of 30. I know this will work. 6 out of 30. Do I skip this one? Yeah, I'll go to this one. I have another 6 out of 30. And a 2 out of 30. Is there any other branches we need to be concerned about? No, because the very bottom of the black branch is automatically goes to yellow. So I'm going to go 6 plus 6 plus 6 plus 2, which is 20 out of 30. Like I said, Mr. Stern. Or 2/3. And then the probability I choose at least 1 yellow. How do I do it? There you go. What? So probability at least 1 yellow. Or 1 yellow. It is. It is. 1. So remember this. This was probability of no yellows. So if I do a 1 minus this, that's going to give me 10 out of 30 or 1/3. So I have a 10/30 probability of doing that. Seem good?
Wait, so for the no yellow one,
Uh-huh.
you wouldn't just like take the like 30 and then subtract the 5 that are like taken up by the yellow, and then you're just done. It wouldn't be. I'm just confused. If you got 20 instead of 25.
Okay, so I'm going to do this. All right, I'm eliminating.
Oh, never mind. I get it.
That branch is eliminated, right?
Yeah.
And then this branch and this branch are eliminated, and we're not even using that anymore.
Okay.
Does that make sense?
Yep.
We good so far? So a tree diagram is a way to go through and think through an event in order to make it work. What do the branches of a tree diagram have to add up to? A whole number, 1. So it has to be, 50 out of 50, 100 out of 100, 20 out of 20. It doesn't matter how many branches you go. I think you can start seeing that a tree diagram doesn't become the greatest way to start representing data. I mean, if we had 3 events taking place, you figure all 9 of those branches, then get 3 more branches. So now I have 27 branches that take place. And it becomes a real big cluster, yucky looking thing. Okay? We good so far? Everyone happy? Hey, what time we had a class? Don't lie. 45? Oh, dude, we got plenty of time.
Wait, no, it's 35, yeah. It's 40.
My eyes on you there, Missy. All right. May I move on? Is that good? So I only have a second example to go over. We good? All right. Let me get through the second example, and then I'll tell you the worst thing I was ever involved in. You like that, huh? Let me get through the second example. I'll tell you the worst thing I was ever involved in.
All right. See what you do now.
No, it is better. You guys are good. I think you guys are going to look at me a whole different light. Huh? Gosh, I wish it was only that. There was a stolen car in there. Then we ran over a cat. I'm just kidding. Lenny's looking at me all. All right. You are going to take a trip. You're going to go take a trip. And you're going to, I don't want to use yellow. There's better colors than that. We can go to Hawaii. Seems good. Go to Mexico. Seems good. Or we can go to Canada.
Oh yeah.
I don't know about y'all, but I might choose to go to Hawaii or Mexico or Canada. Though I was in Banff, Canada this summer. That is a beautiful place. Okay, so it is 60% likely. 60% likely you'll go to Hawaii. 30% chance you go to Mexico. Notice I'm putting these as decimals. Shh, guys being rude. And then 10% chance you're going to Canada. So I put all these as the decimals. So 0.6 plus 0.3 is 0.9. 0.9 plus 0.1 is 1.0. Is this an okay tree diagram so far? Okay. So once we take our trip, there is some chances that the luggage will be lost. Oh boy. Oh boy. The chance you lose your luggage if you go to Hawaii is 30%. So what's the chance that you will have luggage in Hawaii? 70. Good. Okay? The chance that you lose your luggage, wait a minute. The chance you lose your luggage is 30% Hawaii. 45% to Mexico. So what's the chance that you don't lose your luggage if you go to Mexico? 55. Good. All right, and then if you go to Canada, you have a 15% chance of losing your luggage, which means you have an 85% chance that you will have your luggage there. Still with me? So what do I need to do with this? What do I need to do with those branches? Multiply. So 0.6 times 0.3, this is going to give me 0.18. 0.6 times 0.7 is going to give me 0.42. 0.3 times 0.45 is 0.135. 0.3 times 0.55 is 0.165. 0.1 times 0.15 is 0.015. And then 0.85 times 0.1 is 0.085. What do these blues all have to add up to in order to make it a tree diagram? 1. Can somebody verify for me, please? I can go to that 0.18 times 0.42 is 0.5. Oh, it is 0.085. Thank you. That's a 0.085. Thank you. It works? So it's a true tree diagram. All of the outcomes are there. Okay. What's the probability that one of these events will happen? 100%. That's why we wanted to make it to 1. Okay. If you go to Mexico and you lose your luggage, the probability is 1.35. Is that okay? Good. So we're going to Mexico. We're taking this branch here. Lose the luggage. 13.5%. Your luggage is gone. Probability you lose your luggage just on any of the trips. So it's 0.18 times 0.135 times or plus 0.015. Add, what is it? 0.33, which is what percent? Oh man, if you go on a trip, you got a 33% chance. No matter what trip you take, there's a 33% chance you're going to lose your luggage. This isn't good. What's the chance you won't lose your luggage? If it's 33% chance you do lose your luggage, what's the chance you won't lose it? 0.67, which is 67%. Good. What is the probability that you not lose your luggage such that you go to Hawaii? Well, we're going to Hawaii. This is the branch we're staying on. And we don't lose our luggage in Hawaii, 42%. Does that make sense? So we're going to Hawaii. We know that's taking place. What's the chance of losing the luggage? 42%. Or not losing luggage. We're going to Mexico or Canada and not lose your luggage on either. So I'm going Mexico and Canada, not lose, not lose. So it's going to be this one and this one if we add together. Is that right? 25%? So you go to Mexico or Canada and you don't lose your luggage. 25%. All right? Can't read my two. What'd I do? Dude, it's OCD. That's what you should just teach us. Huh? 25%. Okay. You go to Hawaii such that you're lost luggage. So this one's a little different. So letter F says you go probability of Hawaii such that you have lost luggage. Okay? What's my denominator up here? 33. Why 33? We lost our luggage. So lost luggage, I have this, and I have this. For lost luggage, I have to add those up. So that gives me 0.33. Probability we go to Hawaii? 60. Yeah, it's got to be 0.18. So we're going to choose this with that. So we're doing the lost luggage. We know we lost luggage, so we have to have all the lost luggage as 0.33. We're going to Hawaii, and the luggage was lost as 0.18. And that gives me, I got a 54.5%. Okay, so, the 1.5 worksheet, which we'll go over tomorrow. But then also tomorrow there's not a lesson. What it is then it's worksheet 1.6. So it's a review of chapter 1, which we'll work on tomorrow. And then on Friday, we got our chapter 1 test. I know most of you is excited about that. And there's no applause necessary. You just need to throw money. Few things to think about. If you don't have this book yet, let's get it, please. Other things. Let's see. Do I have any meetings today? I don't. I have to be back in this building by 3 to set up girls basketball. But I will be. Should be in my office for the most part. Let me give you, just so you don't waste your time. That's my cell. Text me. Don't text me pictures. Don't joke of the days. I don't need any of that. But if you're going to be coming over to my office and you're not sure if I'm there or not, just send me just a standard text, nothing fancy. Nothing that'll make my phone blow up. Is that right? Just so you know, like if you're like in the East Building and you have to walk all the way there, and you're like, dude, it's snowing in both ways. That way you can kind of have a heads up. Sound like a deal? Now, please don't text me, hey, Mr. Triple, what was the homework last night? I don't know. Okay, it's usually on my desk. Watch the video. Don't text me, hey, I'm running a little late, don't mark me absent. You're running late, you're running late. Dude, what's going on, dude? Sound like a deal?